Hello, I'm your host, Jackie Mullins, and welcome to From Cells to Us. How? Last episode, we watched cells figure out that working together was better than going it alone. We talked about the cheater problem, the cancer problem, the 4 mechanisms that kept cooperation stable. We talked about cadherons and the extracellular matrix and programmed cell death and telomeres. It was a big episode. We watched single cells become something astoundingly new. A multicellular organism, a cooperation of cells that shared interest and shared a fate. And that was roughly 800 million years ago. So what happened next? Well, for 260 million years, evolution started making rough drafts. Multicellular life was figuring out one question. How do you build a body that gets the most food and absorbs the most oxygen? That's it. There was no predators to outrun, no competitors to fight off. Just how do I get more stuff from my environment while lying here? I know a lot of us ask the same questions of ourselves now. So this period had strange, beautiful, deeply confusing organisms, and understanding them is the only way to understand what comes next. Because what comes next is the most dramatic event in the history of animal life on Earth. And that's the Cambrian Explosion. And I know I said last episode that I would do the Cambrian Explosion this episode, but I was writing up the part about the Ediacaran, and I realized it needed its own episode. Because honestly, I shortchanged them completely last episode. I gave them one sentence. Flat, frond-like shapes, paper fans, and then I just kind of moved on. But the Ediacaran is not the story of life waiting around for the Cambrian Explosion. It's the story of multicellular life trying on bodies for the first time. Some were pancakes, some were feathers, some were 3-part spirals. Most of them didn't make it. But for nearly 100 million years, Earth's ocean were filled with life's first strange attempts at becoming something bigger than a cell colony. They deserve more than a sentence or two. Sure, the Cambrian was an explosion, but the Ediacaran was weird, and I am here for it. So here it is, the full story, the calm before the storm. Welcome to Ediacaran Park. Much less running for your life and a lot more asking, what the heck am I looking at here? Let's get into it. Now, before we meet these astounding organisms, I need to revisit something we talked about last episode because there's a bit more to it. Last episode, I told you about Snowball Earth, that it was catastrophic, that most life died, that survivors huddled in refugia around hydrothermal vents, and that the thaw released a supercharged ocean full of nutrients and opportunity, the Aldi Restock Wednesday of geological history. And all that is true, but I feel like I didn't put enough emphasis on why Snowball Earth basically made multicellularity, which recent studies suggest. Because if left in a perfect environment, single cells would have stayed single. They'd be hanging in their bachelor pads, their cheat sheds, eating last night's pizza for breakfast. But when life got hard, when the earth literally froze over, they needed help. Why? Why did they need help in this freezing earth? Well, cold water is thicker than warm water. That's weird, right? But here's how. And when I say cold water is thicker, I don't mean it turns into like slush. I mean viscosity. It's internal friction. Think of it like honey. Honey straight out of the fridge is basically immovable. But the same honey left out on the warm counter, it pours easily. Same molecule, completely different behavior. Water does the same thing. It's just a lot more subtle because it's already a pretty thin liquid to begin with. And we obviously don't notice this. We're pretty big in comparison. But a single cell? Well, for a single cell, this isn't a subtle change at all. Because cells are microscopic, right? And at that scale, water already feels like you're swimming through syrup compared to what we experience. Cold water makes that syrup thicker, even harder to push through, even harder to find food in. Imagine trying to sprint through a pool of honey to catch your dinner, like every day. That takes a lot out of you. That's basically the world a single cell was living in the Snowball Earth. But a cluster of cells, bigger, faster, better at pushing through viscous water, better at capturing what little food existed. So the freeze didn't just kill things. It created selective pressure toward exactly the kind of cooperation we talked about last episode, right? You want someone to watch your back. You need a partner or some buddies to get through this turbulent time. Snowball Earth was basically evolution's Salusa secundus, right? Or Arrakis. Pick your Dune nightmare planet. The things that lived there and survived, because most of them didn't, came out stronger and tougher. Or if you're not into sci-fi, this is like when you forget to water your plant for a few weeks, and when someone asks why it looks that way, you're just like, I'm making it stronger. I'm evolutionary pressuring this son of a gun. So Snowball Earth did the same thing. The catastrophe wasn't just a bottleneck. It was a training camp. And the organisms that came out on the other side weren't just survivors, they were ready. But life got hit twice, right? Bam, bam, just Muhammad Ali and this poor things. Here's why the thaw was just as deadly as the freeze. Because our instinct tells us, well, great, the sun's back. That's good, right? But while the planet was locked in ice, CO2 from volcanic activity had been building up for millions of years with nowhere to go. The world was a shaken Coke bottle with the cap on. And the moment the ice started cracking, the CO2 triggered rapid warming, which melted more ice, which absorbed more heat, which melted more ice. The cap came off and the Coke went everywhere. In geological terms, the planet swung from frozen to hothouse almost instantly. The real killer wasn't the cold. The real killer wasn't the heat. It was the swing between them. Like taking a casserole dish straight out of the freezer and putting it into the 500-degree oven. It doesn't break from the cold. It doesn't break from the heat. It breaks from the sudden change between the two. Or even now, here in the Midwest, it can go from 80 to 50, like you just saw a state trooper on the highway. And all parents know sickness is a big possibility at this time. The freeze killed most things, then the rapid thaw killed what survived the freeze. The organisms that made it through both, that's what we're descendant from. Life that survived Salusa secundus and Arrakis. Not just the tough, not just the adaptable, but both. And for their pains, they were given a food trough with no end in sight and no one to fight for it. You just pick a spot and eat. So what kind of organisms do you think sprang up from this never-ending food trough? Well, that's what we're here to talk about today. But before we meet the organisms themselves, I want to take a moment for the humans who found them. Because for a long time, and I mean a long time, well into the 20th century, scientists assumed Precambrian was essentially devoid of complex life. People were just like, nope, there were weird chains of cells, and then, bam, there was a lot of crazy life. There was nothing in between. Yes, we're sure, don't trouble yourself to look. Which sounds a little crazy, right? But the reasoning made sense on the surface. If complex animals had existed before the Cambrian, there should be fossils. The problem was scientists were imagining the wrong kind of fossil. They were looking for the obvious stuff, right? Bones, shells, skeletons, hard parts, something dramatic, sticking through the geological record, waving its little fossil hand like, hello, Earth to Brent. The Ediacaran organisms didn't have bones. They didn't have shells. They didn't have teeth or claws or hard parts. So of course scientists weren't finding the evidence they expected. They were looking for bones in a boneless world, and when they didn't find them, they thought the world was empty. But the problem wasn't that the world was empty. The problem was that the evidence was softer, stranger, and much easier to miss. But do not fear. This episode will not end here, my fine and loyal listeners, because there was, in fact, complex life. We just hadn't looked in the right places yet. The first major discovery happened in 1946 in the Ediacaran Hills of South Australia. A geologist named Reginald Sprigg, besides sounding like he was born with a monocle, was surveying abandoned mines. He wasn't looking for fossils, he was doing routine geological work. When he noticed something strange in the rocks, these impressions, circular, frond-like disc-shaped impressions pressed into ancient seafloor sandstone. He thought clearly biological, and they were clearly old. So Sprigg published his findings. But on par with many of our themes, the scientific establishment largely ignored him. They were like, what, did you just find a paper fan and push it into clay? This thing is not important. You're stupid. Let's move on. I am paraphrasing here. However, decades later, Similar fossils were eventually found in Namimbia, in Russia, in Canada, and England, specifically in the Charnwood Forest, where a teenager named Roger Mason found impressions in 1957 that turned out to be one of the best preserved Ediacaran species ever discovered, Charnia masoni. Charnia is named after Charnwood Forest in England, and masoni named after Roger Mason, the 15-year-old who found it. Why not just say Mason? Well, because science tries to be fancy sometimes. Like Tom in Parks and Rec, when he pretended the Latin plant names and just said rap artists instead. Soulja Boy Tellums, Bone Thuggin' Harmoniums, and Ludacris's. But why did it take until the middle of the 20th century for someone to find them? Well, there was a few things. One, once again, no one was looking for these kinds of impressions. They were looking for bones. And because most Ediacaran organisms aren't around anymore, they had no idea that these smushes in sandstones were organisms at all, let alone ones from the missing link period before the Cambrian. Two, where all these impressions were found were usually in remote places that keep 558 million-year-old impressions safe. Three, they look like a shell pushed into the mud. They do not look like anything that would be important, right? You're not looking for a skull or a femur bone. You're looking for an organism that is basically alien. Now, you might be wondering, how did these scientists even know these impressions were biological eventually? Like, when did they stop calling Sprigg stupid? Well, when enough fossils were found, similar things started to emerge. These fossils had repeated shapes, growth patterns, attachment points, and in some cases, even movement traces. They showed up in ancient seafloor communities all over the world. And as outlandish as they are, you can figure these things out. Like, if you've ever seen dents in rock, the first one might just be odd. But if you see them in like a left-right pattern, and there's 10 of them, well, then someone walked there. You don't need the whole story to figure that out. You don't need toe prints, right? You can figure out the end of the story with that information. So by the 1980s, the scientific community had accepted what Sprigg had been trying to tell them 40 years earlier. The Precambrian was not lifeless. Complex organisms had existed before the Cambrian, and they were like nothing alive today. Sprigg was right. He was just early. And just to say sorry, they named the period after the hills where Sprigg found them. And so was born the Ediacaran Period. Okay, so very cool. They found these boneless fossils. Boneless fossils. But wait, if they're boneless, how did we find fossils, right? Because normally soft tissue just rots, and if there's no bones, no shell, then there's nothing to leave behind. But the Ediacaran seafloor had something going for it that no later period would have. They just had creatures on top of the seafloor. Nothing was digging through the floor. Nothing had to. There was still that endless trough of food, just flat microbial mats sitting quietly on top of undisturbed sand. When an Ediacaran organism died and got covered by sand or silt, the mat helped seal the body in place. Then microbes started decomposing the body, and that changed the chemistry right around it. Tiny local changes in oxygen, sulfur, iron, silica, and pH, just like making a cast of a gummy worm in clay and then coming back years later. The gummy worm will be gone, but the mold shows what it looked like when it was there. The moment the Cambrian arrived, animals started digging through the seafloor, so there was no time for the hardening to happen. They would get churned up before any impressions could be set. So we have Ediacaran fossils precisely because the Ediacaran world was so peaceful. The silence preserved them, and then the thing that ended their world also ended the conditions that allowed us to find them. Okay, so who were these organisms? What actually lived in the Ediacaran seas? What are making impressions? What kinds of things are being pressed into the sea floor? Well, what we were left with is beautiful shapes, strange shapes that look like life had just discovered the body plan tool and was just like clicking options to see what happened next. And the most famous of these shapes is Dickinsonia. It was oval, segmented, and like ribbed like a leaf. It ranged from a few millimeters to almost 1.5 meters, or for us Americans, roughly 5 feet. So not just a little microscopic blob. This thing could be the size of a human. And for decades, nobody knew what it was. Yes, it had been decided it was biological, stated for the above reasons, but what kind of biological organism? Was it an animal, plant, fungus, lichen, some bizarre dead-end experiment that left no descendants? Scientists argued about Dickinsonia for more than 75 years. Until in 2018, less than 10 years ago, a PhD student named Ilya Bobrovsky went looking for something almost ridiculous. Not just a Dickinsonia fossil, people, no, but one so well preserved that some of its original biological molecules were still trapped inside that rock. Which is an insane thing to look for in a 558 million year old fossil. That's like trying to find a T-Rex fully preserved, or like some of that gummy worm still stuck in the mold clay a million years later. An absurd task, to say the least. But Bobrovsky knew where to look. He went to the White Sea rocks in northwest Russia. Not a vacation site, to say the least. Here the rocks are less cooked, less damaged, better preserved. And the ancient sea floor there had lower oxygen, which slowed decay. Now, going to the White Sea was a very educated guess, but you still cannot underestimate the amount of luck this still needed. So Bobrovsky and his team took a helicopter to remote cliffs along the White Sea. Bear country, mosquito country, accessible only a few weeks a year, descended from the cliff face by rope, hacked out sandstone blocks, dropped them to the beach below, and searched for the right fossil. And they found it. They actually found it. A Dickinsonia fossil preserved well enough that some of its molecules were still there after 558 million years. Can you imagine how careful you'd have to be with that specimen? The pressure to not make one mistake. I mean, that's Jordan hitting the buzzer beater in the championship game. That is so much pressure. So they brought it back to the lab. They carefully dissolved the surrounding rock with acids, extracted the organic material, and ran it through a mass spectrometer. Basically a machine that tells you what molecules are hiding inside your ancient specimen. And what they found was cholesterol. More than 97% of the preserved sterols in Dickinsonia sample were cholesteroids, fossil cholesterol-like molecules. Turns out, Dickinsonia had a large affinity for buttered popcorn, if you could believe it. No, obviously a hilarious joke, but why does finding cholesterol matter? Was it worth the rock scaling in an unforgiving land to get this sample? Well, yes, it was, because scientifically this was huge. The argument that had gone on for 75 years was now solved. Dickinsonia was an animal. Aha! But how could they tell that from cholesterol? Well, think of cholesterol like a biological membership card. Now, every cell has a membrane, right? Your spherical Oreo from episode 1, your bouncer, your boundary layer holding everything together. But different branches of life build those membranes with slightly different chemical ingredients. Plants have their type of membrane, fungi have theirs, algae have theirs, and animals are strongly associated with cholesterol. So when you find a 558 million year old fossil and almost all of the preserved sterols are cholesterol-like molecules, the best explanation is not a fungus, not an algae, not a lichen. The best explanation is an animal. Dickinsonia had the membership card. Now, quick clarification here. That doesn't mean Dickinsonia was 97% cholesterol, like some kind of butter sculpture. It wasn't all membrane. It means that of the molecules tough enough to survive 500 million years in a rock, cholesterol-like molecules were what lasted. That'd be like finding metal hinges and nails after a house burns down. The house wasn't made of metal, right? Metal is just what survived. So Dickinsonia was not a giant cholesterol blob. It was an animal, one of the earliest confirmed animals in the fossil record, living 558 million years ago, about 20 million years before the Cambrian Explosion. The ultimate first draft, and just like most first drafts, it was strange to say the least. Dickinsonia had no mouth, no gut, no obvious way of eating in any conventional sense. The best current idea is that it absorbed nutrients directly through its body's surface, laying flat on the microbial mat and digesting it like from below, like a living pancake just flopping on the ocean floor, or like a Roomba that survives entirely on what it cleans up. But Dickinsonia wasn't the only strange thing taking advantage of the Ediacaran buffet and its zero predator thing. There was also Fractofusus, a flat frond-shaped organism that looked like someone pressed a fern, a feather, and like a fancy pot holder onto the seafloor, and somehow it turned into a living thing. Then there were Rangiomorpha, the Ediacarans fractal like weirdos, branching structures that repeated the same pattern again and again at smaller and smaller scales, like a fern made of ferns made of ferns. Evolution basically found the copy and paste button and was like a kid. It was like, yes, again, press it again. Then there was Cambrian, a slug-like oval about the size of your hand that actually moved, which was very big for this time. The others were very lazy, but Cambrian left tracks and probably scraped microbial mats from the seafloor with a structure near its front end, maybe a mouth. That is also pretty big. Although every time I hear Cambrian, I also hear Clobberella from Futurama. Who does she beat up? You! All right, and then there was Tribrachidium. This was a 3-part radial symmetry, kind of like evolution briefly considered a fidget spinner body plan and then was like, let's delete that. Gave it a whirl, but no. No living animal has a 3-part radial symmetry, not one. So scientists were very confused about these guys, particularly how they ate, because there's no obvious mouth, no jaws, no little Ediacaran fork and knife. Just a classic little 3-part radial symmetry joke for you. So one day, in 2015, a team led by Raman had a very cool idea. Instead of asking only what Tribrachidium looked like, they asked, what would water do when it flowed over this type of body? They used computational fluid dynamics, the kind of software used in aerospace engineering, to model how water would move across its 3 spiral arms. And the results suggested that those arms may have passively funneled water toward the center, trapping food particles like a living whirlpool. They used airplane software to figure out how a 555 million-year-old animal ate its lunch. I love science. And how flattering for the Tribrachidium, right? Like all that work just to see how you ate, buddy. And then there's one more, the smallest, the easiest to miss, and arguably the most important one of all. Icaria wariuta, the size of a grain of rice. Scientists had actually been finding its burrows for 15 years before they found the animal itself. These tiny little tunnels pressed in ancient sediment, clear evidence that something had moved deliberately through the sea floor. Everyone agreed a bilaterian must have made them. But the creature itself was nowhere to be found, just footprints or drag prints. No animal. It took NASA technology to find it, a 3D laser scanner, the kind originally developed to look for signs for life on other planets, scanning ancient rock in South Australia for impressions too subtle for the human eye to catch. And there it was, a grain of rice-sized oval with a distinct front and back, 2 symmetrical sides, and a gut running from one end to the other, a bilaterian. That's the word that matters here. There was a front, there was a back, 2 symmetrical sides, mouth at one end and everything else at the other end, and a gut connecting them. You are a bilaterian. I am a bilaterian. Every vertebrate that has ever lived is a bilaterian. So this grain of rice is possibly the oldest known ancestor to all of us. The thing we can point to and say, yes, this is recognizably on our branch was a grain of rice in the shallow Ediacaran Sea 555 million years ago. And its name, Icaria, means meeting place in the language of the indigenous people of South Australia where it was found. Which kind of feels right? Because Icaria is the meeting place between the alien pancakes and fidget spinners and everything that came after it, between the quiet, ancient sea and you sitting here listening to this podcast about 500 million years later. And they found it with NASA technology in a rock from Australia in 2020. It has been waiting there for 500 million years. So were all of these Ediacaran organisms animals? Did they all have cholesterol? Well, now you see why that question kind of gets complicated. Because look at the range here. Dickinsonia is an animal by chemistry. Cambrian is animal-like, probably because of its behavior. Tribrachidium is an alien body plan with no modern equivalent. Rangiomorphs are still deeply confusing. And Icaria is recognizably bilaterian, meaning it actually starts to look like it belongs somewhere near our branch of the animal story. So the answer is, we're not completely sure. We were extremely lucky with Dickinsonia. That fossil gave us chemistry. It gave us the membership card, cholesterol, the biological signature of being an animal. The others weren't so cooperative. For most Ediacaran organisms, we're back to shape, context, trace fossils, and very educated arguing. But a few things do unite them. They were soft-bodied, no shells, no hard parts, flat or frond-like shapes, maximizing surface area, probably for absorption, feeding, or gas exchange. They were sessile, or at least slow-moving lifestyles, no evidence of high-speed locomotion, and they lived close to the microbial mats, their food source, their world, their buffet. No eyes, no claws, no teeth, no predators that we identify with confidence. Just shapes, pressed into ancient stone, living quietly in the shallow sea, noshing on the open buffet they earned by surviving a planet that already tried very hard to kill them. So those are the organisms. That's the museum tour. That was Ediacaran Park. A pancake, a fern, a scraping oval, a three-armed whirlpool, and a grain of rice that started it all. Beautiful, alien, quiet. But now comes the biology, right? Because the real question is not, what did they look like? The real question is, what were their cells doing differently? Like how on a cellular level were actual bodies being built with different cells doing different jobs instead of just a blob of identical cells all doing the same thing? And this is the part where Ediacaran Period is really amazing. Because yes, the Cambrian Explosion was insane. So much new life. But you can't get anywhere without the first rough draft. Do you think Beethoven wrote Symphony No. 9 on his first try? That Monet painted water lilies on their first try? That I wrote this masterful episode on my first try? We did not. Absolutely not. There are drafts. There were mistakes. There were crumpled pages. There were probably moments where evolution stared at the tribrachidium and went, okay, bold choice, Cotton. Let's see if it pays off. But that is the most important part, right? Putting pen to paper. And that is what the Ediacaran is all about. Not strange shapes for their own sake, but the first serious experiments in building bodies. The first time multicellular life became complex enough that you could look at one part and say, that part is doing something different than this part. The corporation was starting to develop departments. But how? That's the question, right? Because every cell has the same DNA. That's still true, right? Your liver cells and your stomach cells have identical DNA, the same instruction manual. They just have different pages permanently bookmarked. The liver cell opens to the liver chapter and stays there. The stomach cell opens to the stomach chapter and stays there. Neither one reads the whole book anymore. And that's what specialization is. Bookmarking one part in the DNA and just doing that. Different bookmarks, different jobs. And the Ediacaran is where the bookmarking starts to become visible in the fossil record for the very first time. But how do cells know what page to turn to? How do they know where to put their bookmark? It gets complicated as millions of years go by, but at first, you got position. So picture this. You have survived the chill of Snowball Earth and the heat of the Great Thaw. You made it through the freezer and the oven. You are now part of a ragtag team of cells sticking together because being a team works better than going it alone. It's like the Lost Boys, Rufio is probably in there somewhere. And then suddenly, food. A lot of food. Microbial mats spread across the seafloor like an all-inclusive resort for weird soft pancakes. Nobody has invented teeth yet. Nobody is chasing you. Nobody's digging through the sediment. You're not freezing. You're not boiling. For the first time in a long time, life has room to experiment. And when your ragtag team settles down on the microbial mat, little differences start to matter. The cells on the bottom are touching the mat. There are ones facing the water. Some of the cells have their edge exposed. Some are in the middle surrounded. Some are getting more oxygen. Same team, different neighborhoods. And different neighborhoods send different signals. Because cells aren't just little bags of goo, sitting there politely, minding their own business. Cells are covered in receptors, tiny molecular sensors that detect what is around them. And that makes sense, right? Because most of life's history, cells were solo artists. They had to do everything alone, find food, avoid danger, sense chemicals, respond to changes, decide when to move, when to divide, when to hunker down. So they already had all the equipment, receptors, signals, response systems. They were capable solo artists who had suddenly joined a band. Same instrument, new arrangement. So when the ragtag team gets a pay raise, when all that food starts turning into usable energy, they use that old solo cell equipment in a new way. They start communicating. They receive signals. They respond to signals. They send signals back out. And those signals tell each cell which part of the DNA to use. That is the bookmark. The signal tells the cell where to place it. Those signals hit receptors on the cell's surface. The receptors trigger reactions inside the cell, and those reactions eventually reach the DNA, and they say, read that section, ignore that section, make this protein, stop making that protein. Same DNA, different signal, different bookmark, different job. So my best analogy for this would be if you know about Dunkirk or seen the movie Dunkirk, you might remember that there isn't really a single hero. There are officers giving orders, sure, but nobody is standing on the beach with a master plan that saves the day, right? Instead, thousands of people simply start doing what needs to be done. A pilot protects the evacuation. A civilian takes his boat across the channel. Sailors rescue stranded soldiers. Soldiers help strangers into ships. Nobody sees the whole picture. Nobody is in charge of everything. Yet somehow together, they accomplish something extraordinary. That's like what happens when cells first learn to work together. There was no CEO cell, right? No cell standing up and being like, all right, everyone follow me, we're building an animal. Instead, millions of cells began following a few simple rules. Stay together, communicate, share resources, specialize, help the group survive. One cell became better at movement, another one at sensing the environment, another digestion, protection. Each cell only understood its own tiny job. None of them knew what they were building. But just like at Dunkirk, they didn't need to, because when enough individuals cooperate under the right rules, something larger emerges. A city emerges from people, an ant colony emerges from ants, termite mounds from termites, and an organism emerges from cells. The miracle of multicellularity isn't that a leader appeared. It's that a leader wasn't necessary. And just like at Dunkirk, not everyone made it home, but enough people worked together that an impossible rescue became possible. And that's often how evolution works. Multicellularity wasn't perfect. Cells died, mistakes happened, but enough cells cooperated enough of the time that something remarkable emerged, the first true organisms. Okay, but there's a little bit of mystery in this time period, and that is at the end of the Ediacaran, right at the boundary with the Cambrian, approximately 538 million years ago, the vast majority of Ediacaran organisms vanished from the fossil record. Just poof, gone. The beautiful alien shapes that dominated the shallow seas for nearly 100 million years simply stopped appearing in the rocks. So what happened to them? Well, we don't know for certain. It was a very long time ago, but there are a few hypotheses worth knowing. The first was that they were outcompeted. The Cambrian brings the first real predators. More active grazers, more burrowers, animals with shells, animals with claws, animals that could move with purpose. And we have been calling the Ediacarans pancakes, copy and pasted ferns, and a fidget spinner. So let's be honest, not who I'd take in a fight. A body plan optimized for peaceful absorption off a microbial mat is great when the world is quiet. It is a much worse body plan when the buffet becomes a battlefield. The second hypothesis is that they didn't entirely disappear. Some may have just evolved with the times, just like their ancestors did. A few Ediacaran lineages may have changed and adapted and eventually blurred into the early animal groups we started recognizing in the Cambrian. In that version, the Ediacaran doesn't vanish completely, right? It transforms. And the third hypothesis is that some Ediacaran organisms may represent an entirely separate experiment in complex life, a branch of the tree of life that is not our branch, not leading to us, not leading to anything alive today, just an experiment that ran for nearly 100 million years and then ended. Life tried one approach to complexity, found its limits, and pressed refresh. Now, this is just me speculating, but I think part of the answer is kind of hiding in plain sight, right? We already talked about how Ediacaran fossils only survived because nothing was digging through the seafloor. The moment burrowers arrived, that preservation window closed forever. So some of what looks like extinction might just be the record getting destroyed the same time everything else changed. Some went extinct, some adapted, and some just stopped leaving impressions. That's my take, anyway. So a few hypotheses on where the Ediacarans went. We don't know which of these is correct, probably a combination of all three, right? And I feel like some of you might be thinking, let's find some DNA and sequence it, then we can find out for certain. And I love that instinct, just CSI it, right? But alas, no, DNA degrades even under perfect conditions. It has a half-life of a few hundred years. The oldest DNA ever successfully recovered from a fossil is about 1 million years old. Scientists pulled it from a mammoth frozen in Siberian permafrost under absolutely ideal preservation conditions. Cold, dark, sealed away from oxygen for millions of years. And we were thrilled. This was a landmark achievement. The Ediacaran was 550 million years ago. That's not 1 million. That's 550 million years. The mammoth DNA that felt impossibly ancient. The Ediacaran makes that look like last Tuesday. We are not talking about DNA that has degraded. We've been talking about DNA has been gone for so long, the concept of recovering it is the deepest science fiction, which is exactly why the cholesterol discovery hit so hard. Fat is chemically stubborn in the ways DNA simply isn't. It hangs around, it survives, and in this case, it survived for 558 million years inside a rock off a cliff in Russia, waiting for a PhD student with a helicopter and a rope to come find it. So for the Ediacaran, we work with what chemistry is left behind, and we piece together the rest from shape, context, and from a lot of very educated arguing. Just scientists shaking their fists at each other, clutching pipettes. And that happens a lot. Even with other things more recent. You know, my son has moved from dinosaurs and we are on to the megalodon era. He got a fossilized megalodon tooth for his birthday and it goes everywhere with him. He asked me to show him a megalodon fossil and I was like, oh, sorry, buddy. You know, they're all cartilage, no fossils, but I'll look up the jaw for you. So I Googled it, as any awesome mom with a science podcast would, only to discover the jaws of sharks are cartilage too. After the kids sang a particularly pitchy chorus of "We thought mom was smart," I did more research. And as it turns out, basically all we have are teeth. But scientists have found a few vertebrate pieces and rare cartilage traces. But, you know, no giant museum-ready jawbone. I was kind of like upset by this. Like, have you been peddling this giant shark all this time and you don't even really know? They made a movie about it and called it The Meg, when the word megalodon is literally the coolest name ever. It's foolish. So I dug further and found out that from those teeth alone, scientists figured out that megalodon was up to 60 feet long, weighed 48 tons. How? Because tooth size scales proportionally with body size in sharks, so they measured the teeth, compared them to modern great whites, and did the math. They also found that whale bones with megalodon bite marks and actual tooth tips embedded in them. That's how they confirmed what they ate. Just teeth, and we built this whole picture from that. So if scientists can reconstruct a 60-foot shark from a handful of teeth, piecing together the Ediacaran from chemical traces and rock impressions, though still much older and much more wild, it does start to feel maybe a little less impossible. Okay, so here is where we stand. 635 to 538 million years ago, a world of shallow seas and microbial mats and strange flat organisms absorbing nutrients through their skin. The first serious experiments in body plans, the first cell differentiation at scale, the first organisms large enough to leave a fossil record. Beautiful, alien, peaceful, and then silence. The Ediacaran organisms disappear, the microbial mats are disrupted, the fossil record shifts, and what replaces them is so different, so sudden, so explosive that scientists have been arguing about it for a century. Because 538 million years ago, something happened that changed everything. Eyes appeared, shells appeared, claws appeared, predators appeared, prey appeared. Lots of things appear. The whole terrifying, beautiful machinery of complex animal life, essentially all of it, showing up in what geologists call an instant. The quiet is over. Next episode, we talk about the Cambrian Explosion. what caused it, who showed up, why it happened so fast, and why a small, unremarkable swimmer named Pikaia matters more than you think. That's episode 14, Life Goes Feral. Now, quick note, I apologize again for the time it took me to get this episode out. Honestly, I just couldn't get it right. And then we had our power go out, and I lost the whole document, which I didn't even know, still happens in 2026. I should have saved it. I know, that was my fault. And also my son got mono. He's 1. How does that even happen? Anyway, I apologize for its lateness. Okay, so don't forget to follow, like, and comment. I would very much appreciate it. And thank you so much for joining me on this biological journey. I'm Jackie Mullins, and this has been From Cells to Us. How? I'll see you next time.